efficient validation and verification. Hashing and asymmetric key encryption. These techniques depend on several complex proven algorithms. We'll provide a high-level view of the application of these algorithms and the critical role they play in securing the decentralized chain in the 4 lessons of this module, namely public key cryptography, secure hashing, transaction integrity, and block integrity. We'll begin this module by discussing the concept of asymmetric key encryption. Then we'll define the concept of hashing, followed by the algorithms used for various hashing needs of the blockchain protocol. We then explain the techniques that use these algorithms to manage the integrity of the transactions and the blocks in a blockchain. Learning outcomes of this module are to summarize the working of the public key cryptography, explain simple hashing and Merkle tree hashing, explore the application of hashing and cryptography in protecting the blockchain. Recall that blockchain's decentralized network participants are not necessarily known to each other. Credentials cannot be checked by the conventional means such as verifying who you are with your driver's license. Participants can join and leave the chain as they wish. They operate beyond the boundaries of trust. Given this context, how do you identify the peer participants? How do you authorize and authenticate the transactions? How do you detect forged or faulty transactions? We can do these things by using public key cryptography algorithm that we'll discuss in this lesson. Let's begin by examining simple symmetric key encryption. The same key is used for encryption and decryption, so it is called symmetric key. Example: Caesar encryption is the simplest one where alphabets of a message are shifted by a fixed number, and this number is called the key. In this example, f is a function defined by shift by 3 an alphabet. Consider meet me at the cinema. You shift by 3 the ASCII value of every letter to encrypt it, and your receiver decrypts it using the same 3 as the key. Shift the other way every character to view the original message. 3 is the key in this trivial example. Since the same key is used for encryption and decryption, it is a symmetric key. Note that the key and the encryption and decryption functions are typically much more complex in a real application. Note that symmetric key encryption has issues. Number 1, it is easy to derive the secret key from the encrypted data. And number 2, the key distribution. How do you pass the key to the participant transacting? These issues are further exacerbated in a blockchain decentralized network where participants are unknown to each other. Let's now examine how public key cryptography addresses these issues. Instead of a single secret key, it employs 2 different keys that take care of both the issues of symmetric key encryption. Let lowercase b, uppercase b be the private public key pair for a participant in Buffalo, New York, USA. Let lowercase k and uppercase k be the pair of keys for the participant in Kathmandu, Nepal. Public key is published. Private key is kept safe and locked, typically using a passphrase. And the pair works as follows. Encrypting function holds 2 properties for the key pair. The public key private key pair has the unique quality that when a data is encrypted with the private key, it can be decrypted with the corresponding public key and vice versa. Now let's look at an example. Authenticate the sender and the receiver. We'll examine just one common use of asymmetric key encryption. Let's say a participant in Buffalo wants to transact with a participant in Kathmandu. instead of sending just a simple message, a participant in Buffalo will send a transaction data encrypted by Buffalo's private key and then encrypted by Kathmandu's public key. Kathmandu will first decrypt the data using its own private key, then use Buffalo's public key to decrypt the signed transaction data. This ensures that only Kathmandu can decrypt and receive the data, and that only Buffalo could have sent the data. A popular implementation of public key, private key is the Rivers-Shamir-Edelman RSA algorithm. Common application of RSA is the passwordless user authentication, for example, for accessing a virtual machine on Amazon Cloud. Though RSA is very commonly used in many applications, blockchains need a more efficient and stronger algorithm. Efficiency is a critical requirement since public key pair is frequently used in many different operations in blockchain protocol. Elliptic curve cryptography, ECC family of algorithms, is used in the Bitcoin as well as in Ethereum blockchain for generating the key pair. Why ECC, not RSA? ECC is stronger than RSA for a given number of bits. Did you know that 256-bit ECC key pair is equivalent in strength to about 3072 bits of RSA key pair? Both Bitcoin and Ethereum use ECC-based algorithms for their encryption needs. Why should we learn about encryption and hashing? You may ask. The private-public key pair is a metaphorical passport to participating and transacting on the blockchain. Similar to how you learn to use a credit card, secure it and protect it, you need to protect the private key for the security of your assets on the blockchain. In this lesson, we learn hashing that plays a critical role in the blockchain process, and also in the integrity of the transaction and confidentiality of data. You'll keep hearing the words hash rate, hash power, hash this, hash that frequently in the blockchain world. For these reasons, you ought to have some basic understanding of hashing techniques. The primary goal of this lesson is to provide you with this knowledge. What is hashing? A hash function or hashing transforms and maps an arbitrary length of input data value to a unique fixed length value. Input data can be a document, tree data, or a block data. Even a slight difference in the input data will produce a totally different hash output value. The following are two basic requirements of a hash function. The algorithm chosen for the hash function should be a one-way function, and it should be collision-free or exhibit extremely low probability of collision. The first requirement is to make certain that no one can derive the original items hashed from the hash value. Can you make potatoes out of mashed potatoes? The second requirement is to make sure that the hash value uniquely represents the original items hashed. There should be extremely low probability that two different data sets map onto the same hash value. These requirements are achieved by choosing a strong algorithm such as secure hash and by using appropriately large number of bits in the hash value. Most common hash size now is 256 bits, and the common functions are SHA-3, SHA-256, and Kechak. Hash value space. How good is 256 bits hash? A 256-bit hash value space is indeed very large. 2 to the power of 256 possible combinations of values. That is approximately 10 to the power of 77. That is 10 followed by 77 zeros. Odds of a meteor hitting your house is higher than generating two of the same hash values of 256 bits when applying this algorithm. Great. Let's proceed to explore some techniques now. We'll compare two different approaches for hashing based on how the constituent elements are organized: a simple hash and a Merkle tree hash. Here we illustrate simple hashing and Merkle tree hashing with add as a hash function. We use the data 10, 4, 6, 21, and 19 and add as a hash function. Actual hashing functions are quite complex and are variations of SHA-3, and the data values are much larger, many 256 to 512 bit values. In the simple hash approach, all the data items are linearly arranged and hashed. In a tree-structured approach, the data is at the leaf nodes of the tree. Leaves are pairwise hashed to arrive at the same hash value as a simple hash. When is a tree-structured hash used? When is a simple hash used? When we have a fixed number of items to be hashed, such as the items in a block header, and we are verifying the composite block integrity and not the individual item integrity, we use simple hash. When the number of items differ from block to block, for example, number of transactions, number of states, number of receipts, we use the tree structure for computing the hash. Note that the state is a variable that may be modified by a smart contract execution, and the result of the execution may be returned in a receipt. We learn more about their use in Course 2. Tree structure helps the efficiency of repeated operations, such as transaction verification and the state changes from one block to the next. Log n versus n. Summarizing, in Ethereum, hashing functions are used for generating account addresses, digital signatures, transaction hash, state hash, receipt hash, and block header hash. SHA-3, SHA-256, Kechek-256 are some of the algorithms commonly used for hash generation in blockchains.